This podcast is on orbitals and the covalent bond. The overlap of atomic orbitals from separate atoms produces molecular orbitals when a bond forms. You see, each molecular orbital, like an atomic orbital, has room for 2 electrons. There are 2 types of molecular orbitals we're going to consider. One of which is called a sigma bond, where the bond is on the axis between the atoms, and the other is the pi bond, where the bond is above and below the axis between the atoms that are bonding. The sigma bond is produced when orbitals from 2 separate atoms overlap. And they overlap, and once they overlap, they rearrange, and they become the sigma bonding molecular orbital. Now, you can also have p orbitals on separate atoms, and those p orbitals on separate atoms can also come together and overlap and form the sigma bonding molecular orbital between the 2 p's. Now, pi bonding also involves p orbitals. Again, the p orbitals are on separate atoms. They come together and then overlap and form the pi bonding molecular orbital, which is above and below the axis between the 2 atoms. While there are 2 lobes to it, it is only 1 bond. Now, all single bonds are sigma bonds. A double bond is composed of 1 sigma and 1 pi bond, and a triple bond, you're right, is 1 sigma and 2 pi bonds. Well, this is great, but atomic orbitals don't really work to explain molecular geometry, so we need to take a good look at this. You see, in methane, in Chemistry 1, you correctly predicted the shape to be tetrahedral using the electron domain theory, where the electron domains all repelled each other to give the tetrahedral structure. But if you look at carbon, it's got 2 valence electrons in an s orbital that are paired, and 2 in a p orbital, and those p orbitals are at right angles to each other, so the bonding should be. So how do you get tetrahedral out of this? Well, because the atomic orbitals change when making a molecule as the molecular orbitals form, we can sort of explain it. Sort of, because we use what's basically an invention of some chemists. It works. We blend the s and p orbitals of the valence electrons and end up with the tetrahedral geometry. What you do is you take 1 s and you take 3 p's, and it's almost like you throw them in the blender and spit out 4 sp3 hybrid orbitals. You look at the graphic from Zumdahl, you've got the red s orbital and the 3 blues, and they end up mixing completely and forming 4 sp3 hybrid orbitals, which are 109.5 degrees away from each other. If you look at this methane mock-up molecule, what you have is the tetrahedral structure, where the hydrogen 1s orbital is overlapped with the sp3 orbitals to share the electrons to form methane. And in terms of energy, it also works. If you hybridize a 2s and a 2p, you get 4 sp3 hybrid orbitals at energy a little below the p and a fair bit above the s's, because you're blending them, and the whole thing works. How do we get there? Well, we know the geometry of the molecule from experiment. We also know the orbitals that are on the atom, and hybridizing orbitals can explain this geometry, so if the geometry requires a tetrahedral shape, we state that it is sp3 hybridized. This includes bent, by the way, and trigonal pyramidal molecules, because in the case of the trigonal pyramidal, something like ammonia, one of the sp3 lobes holds the lone pair. And in the case of water, on the oxygen, we have 2 sp3 lobes holding the lone pair. Well, what about other kinds of hybridization? The ethene molecule has a double bond. And in electron domain theory, or VSEPR, the double bond X is 1 electron domain, and we say that this molecule is trigonal planar. Well, how do we end up with 3 blended orbitals? We use 1 s and 2 p's, and we make the sp2 orbital. That leaves 1 p orbital perpendicular to the structure, and you'll see later. one s, two p's, put them together, and we get the 3 sp2 hybrid orbitals, and they're all at 120 degrees to each other. In terms of energy, it's the same idea. The hybridization gives us sp2. We also have the 2p, one of them left over. And you'll notice the energy of the hybridized orbital is slightly less because it's got more s character and less p character than the sp3. Well, where is that extra p orbital? It turns out that it is perpendicular to the plane of the 3 sp2 hybrid orbitals that are 120 degrees. And when the overlap of the orbitals makes the sigma bond, the sp2 orbitals, okay, you're left still with that p up there. Well, there happens to be a p on each one. And so the sigma bond is the green overlap there in the middle. And then what we find happens is the pi bond forms above and below the atoms between the adjacent p orbitals. And you'll notice they've got the dotted lines there in the drawing out of Zumdahl. The two bonds of a double bond are the 1 sigma and then the p orbitals overlapping to give the pi bond. That, yeah, I know sort of looks like it's more than one bond, but the double bond is composed of that 1 pi, 1 sigma, and the pi actually has a region above and a region below, but it's just the one bond. This has been sometimes an issue, so make note of this. That's only 2 bonds in that graphic on the bottom right. Well, with sp2 you've got 3 things coming off an atom, and the structure is trigonal planar with 120 degree angles. If you have one bond that's pi, one bond that's sigma, and one lone pair, you'll end up with something like ozone, which is going to be bent. Or if you have one pi bond and 2 sigma bonds, you'll have a structure like our ethylene molecule, or formaldehyde, or some other molecule. What about 2? You knew this was coming. 1s and 1p hybridized, we end up with a linear structure. We call it sp. The bond angle between it is 180 degrees. Okay, those 2 lobes, they're going to be as far apart. They do obey the electron domain theory. The p orbitals you'll see below are at right angles to each other, and so that makes room for 2 pi bonds and 2 sigma bonds on each one. You can have a triple bond to another molecule, another atom, like nitrogen between the 2 ends, or 2 double bonds like the carbon in the middle of carbon dioxide. In terms of energy, the hybridization gives us the same thing with an s and a p, and we're left over with 2 p orbitals now that are not involved in the hybridization, and the energy diagram, again, is accurate and works. Look at carbon dioxide that I mentioned earlier. Carbon can make 2 sigmas and 2 pi's. Oxygen can make 1 sigma and 1 pi, and you end up with the carbon dioxide structure. And if you were to build it using the springs and in the molecular model kit, you will see that one of the sets of springs go up and down, the other set goes sideways. You may have noticed that. This is the hybridization is the reason, one of the reasons we propose to explain it. I also mentioned nitrogen. Here we have the sigma bond between the 2 ends, and then you have 2 pi bonds to make that triple bond once again. There's your overlap of your sigmas, and the p's can overlap. So much just a closer up view of it. Well, we also can break the octet rule. Phosphorus pentachloride is a well-known material. The model predicts that we must use the d orbitals, and so we suggest that we have dsp3 hybridization. Now, there is some controversy about whether or not this is actually occurring. It is at the forefront of some chemical research right now, but for the purposes of the AP course, we're still using it. So what you end up having is 1d, 3 p's, and 1s, producing a trigonal bipyramidal structure of dsp3 hybrid orbitals. They can only sigma bond, and you end up with something like PCl5, and there are other shapes that you probably did when you did electron domain theory for geometries, like the seesaw or the T-shaped, but that is the dsp3 hybrid orbital. Finally, you look at PCl5. We can't really tell the hybridization of the chloride, but we might assume sp3 to minimize the repulsion of the electron pairs. This is sort of the theory stuff that chemists love to get into. Finally, D2sp3, the octahedral structure or the square bipyramidal structure, depending on what you want to call it. 2 Ds, 1 S, 3 Ps, put them together, you get 6 hybrid orbitals, and this is how we can put together something like SF6. It gets us up to 6 things, or a square planar molecule. It is said to be octahedral. Again, we can only have sigma bonds here with the octahedral structure, and like the DSP3 trigonal bipyramidal structure, there is some controversy about whether or not this actually occurs in hybridization and in bonding. But that is a good overview of hybridization and the formation of both pi and sigma bonds for you.